So the ninth question here is, a drawer contains 2 blue, 4 red and 2 yellow balls, right? No 2 balls have the same radius, which means every ball is distinct. This is another way of saying the same thing, that each ball here is distinct because each of them has a different radius. I can uniquely distinguish each ball. If 2 balls are randomly selected from the drawer, what is the probability that they'll be of the same color? Very simple question if you think about it, right? So what is the total number of balls that I have? I have a total of 8 balls, right? So I can choose 2 balls. So what is the probability if 2 balls are randomly selected, right? So in how many ways can I select 2 random balls from these 8 balls? I can choose in 8 choose 2 ways, right? This is the total number of ways I can choose 2 balls. Now it says what is the probability that if I randomly select they'll be of the same color? So same color can happen in 3 ways. Both balls can be blue. Look at this, both balls can be blue, which means I can choose 2 blue balls in 2 choose 2 ways. I can choose 2 red balls. In how many ways can I choose 2 red balls? 4 choose 2. I can also choose 2 of the yellow balls, right? So the total probability is this, right? See, if this is the number of ways I can choose 2 out of 8 balls. This is the number of ways I can choose 2 blue balls. This is the number of ways I can choose 4 red balls. This is the number of ways I can choose 2 yellow balls, right? So this is the number of ways, the sum of all 3 is the number of ways I can choose such that the balls are of the same color. So if you simplify this now, 2 choose 2 is 1, 4 choose 2 is 6, 2 choose 2 is 1 by 8 choose 2. What is 8 choose 2? 8 choose 2 is 8 into 7 by 2. So this is 4, 28. So you have 8 by 28, which is nothing but 4 2s and 4 7s, 2 by 7. So the answer here is very simple, 2 by 7. Very simple question. And this whole probability, this is a simple combinatorics problem posed as a probability problem. Right? Again, you will encounter many similar problems in the actual test also. So let's look at the 10th question now. It says, it will rain. So John says it will rain tomorrow. So let me write this as John says it will rain, just as a short form. And Amy says it won't rain. So Amy says not rains, right? So they've made these 2 statements already. These 2 statements have been made. In general, John and Amy are right about the weather with 70% probability and 60% probability respectively, and independently, right? So they both are independent events. So John saying that it will rain is independent of Amy saying it won't rain. They're completely independent events. So given the conversation above, what is the probability that it rains tomorrow? So let's try to write it as a probability statement. That's where the challenge here is. Probability it rains given, look at this, once you write it as a probability statement, then everything will follow from simple theorems and properties that we have learned. So probability it rains given that John says that it rains and I write it as intersection, and Amy says it will not rain. So some books write it like this. Some other books also, instead of using intersection here, they'll write it as comma. So when they say comma, it means and, right? So this is a more popular notation. You'll see this in many textbooks. So this is conditioned on this and this, both of them happening. So if you look at the conditional probability formula, think about it. And there are only 2 possibilities, right? Either it rains or it not rains. There are only 2 possibilities. So this I can write it as simple Bayes theorem. Probability that it rains and my John said it rains and Amy said it says not rains. This intersection by probability that Jamie says it rains and Amy says it doesn't rain. Look at this. That's what this probability here is. Now if you think about it, this probability is simple to compute. What is this probability? Let's think about this, right? So again, John is correct 70% of the times, Amy is correct 60% of the times. What is the probability it rains when John says it rains? When John says it rains, he's correct 70% of the times. So the probability that it rains when John says it rains is 0.7. And look at this, these two are independent. It says, look at this, they're respectively the probabilities and then independently the probabilities, right? They're independently also the probability. This is very important. Without this independence, this whole thing, it's hard to compute this. Now, given this, so because they're independent, I can just multiply them. Now, probability that it rains and Amy says it not rains. What is that probability now? So probability that it rains and Amy says not rains. Amy is correct 60% of the times. If it rains and Amy says it doesn't rain, that means Amy is incorrect. Amy is incorrect 40% of the times, which means this is now 0.28. This is simple. But how about this? How do I compute this now? This is slightly tricky. So what I'll do here is, I know that there are only two possibilities, rains or not rains. So I'll write this as probability that it rains, intersection, John says it rains and Amy says it doesn't rain. And these two, either it rains or it doesn't rain, right? They're mutually exclusive events. Only one of them can happen. Plus probability that it not rains, and John says it rains and Amy says it doesn't rain. This probability can be written as sum of these two probabilities. Now let's work out what these probabilities are, right? So if you try to work out what these probabilities are now, what is this probability? If you think about it, probability that Jamie says it rains and it rains and Amy says it, so this is same as this probability, right? This is exactly same as this. So this is 0.28 plus, what is this probability? So here Jamie says rains and it doesn't rain. Sorry, Gemini. I think I'm too much stuck on the Game of Thrones, right? This is not Jamie, this is John, sorry. I'm too much stuck on the Game of Thrones names, I think, okay? So John says it rains. Let's say J says it rains. J basically is for John, right? John says it rains and it doesn't rain, which means John is incorrect. So John is correct 70% of the time, so he's incorrect 30% of the times. And it also doesn't rain and Amy says it doesn't rain. So Jamie is correct. Amy is correct, not Jamie. Amy is correct. I think I'm getting confused between John and Amy because there is a character in Game of Thrones called Jamie. I think that's the reason. That's why I'm getting confused with this. Anyway, not rain and Amy is correct. Is 60%, right? So now what do we have? We have 0.28 by 0.28 plus 0.18. Now if we simplify this, this is 28 by 28 plus 18. Now if we simplify this, this is 14, this is 14 and this is 9. Right? So 14 by 14 plus 9, which is 14 by 23. This is the answer here. Right? Very good question. This is an application of Bayes' theorem. Again, the challenge here, the very interesting challenge here is translating the problem into the mathematical equation and then step by step simplifying it. Coming up with these numbers is the easy part. Writing it as a conditional probability carefully, because many people mess it up, especially this problem, because there are two events here. Nothing stops us from having two events, right? An event can be conditioned on two or more events. We have seen this also in the course videos, right? An event can be conditioned on more than two events, more than one event here. We have seen this form of Bayes' theorem also in the course videos. So now let's look at the 11th question. If the probability density function, the PDF of a continuous random variable, and this random variable will take values from -1 to 7, if it is given by this. Look at this, there is a constant a and we are not given what the value of constant a is. Then what is the value of probability that x lies between 0 and 4? So one of the properties that we have discussed of a probability density function is this. If I'm given a PDF, this integration of PDF from -infinity to +infinity has to be equal to 1, right? So because look at this, what is this? This is the probability. This is the probability that the random variable x lies between -infinity, sorry, not equal to. It's a probability that the random variable lies between -infinity and infinity. This has to be equal to 1, right? Obviously, because it's a continuous random variable. Now, since x cannot take values outside of this range, I can write this as integral -1 to 7 f of x. What is f of x? A into, I'll take the a outside because it's a constant, right? I can write this as x square minus 6x minus 7. Look at this, I'm just multiplying these two. Dx has to be equal to 1. Now, if I solve this, I can compute what a is, right? If you think about it, if I solve this, I can compute what a is. Standard integration, very simple integration to perform. So what is the integral of this? A, x cube is x for x square, x cube by 3 minus, what is this? This is 6 into x square by 2. So 3x square minus 7x, and this integral is from -1 to 7 equals to 1. So now if I simplify this, again there will be a constant, but the constant will get cancelled out. This is definite integral and not indefinite integral, right? So this is equal to 3. Now if I simplify this, I'll get, if I solve for this, I'll get a equals to -3 by 256. Again, simple algebra, right? If see, I had to place x equals to 7, x equals to 1. Just solve this expression. Standard definite integral problem, you get a. Now when you get a, you got your a, right? Now the question here is, what is the probability that x lies between 0 and 4? Now how do you compute that? Again, it's very simple to compute. It is this integral 0 to 4 f of x. What is f of x now? Minus 3 by 256, which is your constant, x square minus 6x minus 7 dx. This is what it is. And we already have the integral, right? So this is nothing but minus 3 by 256, the integral of this, which we have written here, right? X cube by 3 minus 3x square minus 7x from 0 to 4. That's it. If you now simplify this, you will get a value of 41 by 64. Again, the computations here are slightly tedious and time taking, but they're simple. The problem here itself is simple. The only trick in this problem is a value is not given. And if you look at all the options here, a is not used as a constant anywhere, which means we have to first determine a. And how do you determine a? You have to just know this property of about a probability density function that we have discussed in the course videos, right? So if you know this property of a PDF, only functions which satisfy this are valid PDFs. Using that property, we computed what a is. Once I know a, computing this probability is nothing but a simple integration, right? Good problem. So let's look at this question. This is a slightly intricate question, but try to follow the logic that I go with it and we'll be able to solve it, right? There are 16 players, P1 to P16. This is actually 16, okay? Not P16. This is P16. This has to be in the subscript. So 16 players play a tournament. They are divided into 8 pairs at random, right? So they're divided into 8 pairs at random. From each pair, a winner is decided on the basis of the game played between the 2 players of the pairs. Perfect. Assuming that all players are of equal strength, which means their probability of winning is same, right? Given any pair. The probability that exactly one of the 2 players P1 and P2 is among the 8 winners, right? So I'll break this into 8 pairs, right? I'll break this into 8 pairs. So it says only one of these 2, either P1 can be there in these 8 winners or P2 can be there in these 8 winners. What is the probability of that? So now, because these 16 players are paired, right? So there are 2 possibilities. Let me write down, again, I'll try to write the equations and some stuff so that it's easier for you to connect the dots. So let's say E1 is the event. Okay, let's define some events so that we can go into the mathematical space and understand this. Actually, a good part of the challenge here is to define these events carefully, right? So E1 is the event, right? That P1 and P2 are paired together. So P1 and P2 are together. So if they're in a same set, look at this, if they're in a same pair, if P1 and P2 are together in a pair, then only one of them wins. Very good, right? Obviously, then your problem is solved. But there is a second case where they're not together. They're in 2 different, so P1 and P2 are not together, right? This is also possible, right? So we have to, again, if they're together, it's very simple. Then only one of them will win. If they're not together, even in such a case, we have to compute the probability that only one of them wins. And we have to sum up these 2 effectively. At the end of it, that's what we will do, right? So first of all, let's compute this, right? What is the probability that P1, so what is probability of event E1? Event E1 basically means P1 and P2 are together. What is the probability? Look at this. P1 and P2 have to be paired up together. P1 can be paired up with any of the other 15 people. If you look at it from P1's perspective, he can be paired up with any of the other 15 people. Of these 15 people, for him to be paired up with only P2, there is 1 by 15 possibility. Right? The probability here is 1 by 15. The probability that they're not paired together is nothing but 1 minus 1 by 15. This is 14 by 15. So let's keep this here. This is the first step, right? Now let's see. In case E1 occurs, okay, let's also define an event, right? Let's also define another event A. Let's say event A is the case where exactly one of them wins. Let's just define that, right? Exactly one of P1 and P2, one of these 2 people wins. Now look at this. What is the probability of A given E1? This is very simple, right? Probability of A given E1 is they both are together and we know exactly one of them has to win. What is the probability that exactly one of them wins if they both are together? This is obviously absolutely true. This is always 1, right? So this part is taken care of. Now we have to compute the probability of A given E2. So this is the tricky part, right? So what is this? Now if I try to break this up, right? If I try to break this up, this is nothing but probability of A intersection E2 by so this is probability of A intersection E2 by probability of E2, right? If I can somehow compute this, I'm more or less done, because what do I want to compute finally? I want to compute probability of A. See, my problem here is probability of A. That's what I want to compute. Probability of A I can write it as, because either E1 can happen or E2 can happen. Only one of these two can happen, right? Only one of these two can happen. So I can write this as probability of A given that E1 has happened plus probability of A given that E2 has happened. Now this is simple. This I can write it as probability of A given E1 into probability of E1 plus probability of A given E2 multiplied by probability of E2, right? So this part, now if you notice, this part is simple. What is the probability of A given E1? This is equal to 1. What is the probability of E1? We already computed that, right? 1 by 15. What is the probability of E2? 14 by 15. Now, what is the probability of this? If I can compute somehow this probability, my answer is solved, right? So what I want to compute right now, probability of A given E2, which I can write it this way also. But let's try to think about what it means. It means probability that exactly one of them wins. The challenge here is probability that exactly one of them wins, given that they are in two different sets altogether. Okay. So now let's see. So let's see. So what does this mean? This means they are in two different sets. That's all it means, right? So what I want to compute, again, I have this here. I'll come back to this, right? Probability of A given E2, which means they are in two different sets, right? Or two different pairs. This is nothing but probability of, so let's say P1 wins. I'll write P1 wins as P1. P1 wins and P2 does not win. So let me write it this way. Okay, look at this. They're in two different sets, right? They're two different sets, which means P1 winning has got nothing to do with P2 winning. So I can write this as probability of P1 wins and P2 loses and union probability of P1 loses and P2 wins. Look at this. There are two ways, right? The two ways that this can happen. Again, I'm not defining it in terms of a slightly different set of events. But logically, if you think about it, the probability that only one of them wins, given that both of them are in two different pairs, is probability P1 wins and P2 loses, union probability P2 loses and P1 wins. Now, since these two are independent events, look at this, or not independent, sorry, these two are mutually exclusive, right? See, this can happen. In this, P1 wins and P2 loses. In this, it's the exact opposite. P1 wins, so these are not independent, these are mutually exclusive events, right? Since these are mutually exclusive, if you think about these events, they're mutually exclusive like this, not independent. Again, I also sometimes get confused. So if you think about P1 intersection P2 bar, this is one event wherein P1 wins and P2 loses. Here P1 loses and P2 wins. There is no intersection between both of them, right? So and I'm trying to compute the union. So probability of A union, look at this, probability of A, actually instead of this, so actually I should write this as not at this, sorry. So I should write this as, sorry, my bad, there is a small notation mistake here. This union this is the total probability that I want to compute, right? Not the probability. So probability of A union B, if A and B are mutually exclusive, is probability of A plus probability of B. So P1 wins and P2 loses plus probability of P1 loses and P2 wins. Okay, we're making some progress, right? Now P1 winning and P2 losing are completely independent. These are two independent events because they're in two different pairs. Look at this. If they were in the same pair, if one wins, the other loses. But here they both are in two different pairs, right? So P1 winning and P2 winning are completely independent events. So probability of P1 into probability of P2 bar plus probability of P1 bar into probability of P2. Now if you notice, because it says every person is of equal strength, right? There is equal probability that everybody wins. So this is half, this is half. So probability that P1 wins is half, right? Now probability that P2 wins or P2 loses is also half. Plus again, this is half and this is half. So 1 by 4 plus 1 by 4, this is equal to half. So probability that exactly one of these two people win, given that they're in two different pairs, is half, which means this probability now is half. Now let's simplify the whole thing, right? Now if you simplify the whole thing, you have 1 and 1 by 15. So you have 1 by 15 here, plus you have 7 by 15 here. 2 and 14, so they cancel out and you get 7 by 15. So the answer now is 8 by 15. Again, this is a slightly involved question because there are many steps here. I hope I convinced you step by step. Again, the challenge here is taking a real world problem, writing it into events carefully. Very, very important step. Defining each of these events carefully and thinking from again, look at this. What did we apply here? We simply applied basic probability concepts, what we learned, right? But oftentimes people will come till here and they'll get stuck here. They'll not think how to compute this now. I've seen a lot of people, this problem, right? They come till here and here they get stuck. They're not able to compute this. Here you again have to think differently. Okay, what is the probability that exactly one of them wins, given that they're in two different pairs, which means one of them wins, one of them loses, or this guy loses and this guy wins. And these two events are mutually exclusive. That's why you should be able to add it. And these two events are independent. That's why you should be able to multiply. Right? Again, these are simple properties of probability that we learned in the course videos. So this is a slightly involved, slightly hard question, but a very good one nonetheless. So let's look at the next question here. It says, a man is known to speak truth 3 out of 4 times, which means the probability he'll say truth is 75%. He throws a die and reports that it is 6. Right? He throws a die and says it is 6. Find the probability that it's actually 6. Again, whenever you look at a problem like this, this is a standard Bayes theorem type of problem. So let me define a bunch of events, right? So let me say an event E. Let me define an event E as let event be that the man reports that 6 occurs, right? So he says 6 occurs. So the man says dice equals to 6. The dice is 6. Okay, let me write this in English, right? So that it's easy. Let's say S1 is the event that dice is actually 6. Right? The dice is actually 6. Okay. Let's say S2 is dice is not 6. So dice is not 6. Right. Now if you think about it, what is probability? So now the moment you define this, you can use all of conditional probability and Bayes theorem. Now what is given to us? So we know probability of S1 because it's a fair dice, right? Probability that dice is 6 is 1 by 6. Probability that it is not equal to 6 is 5 by 6. Now if you think about it, either S1 has to happen or S2 has to happen, right? They're mutually exclusive and exhaustive, which means either S1 has to happen or S2 has to happen, one of them. So what do we want to find? Find the probability that it's actually 6. So we want to find the probability, right? Find the probability that it is actually, the dice is 6, given that he throws a dice and reports that it is 6. Given that he says it is 6. This is the probability that we want to find. Right? He throws a dice and reports that it is 6, which is what we called as event E. And how did we define this event? Because this event already happened. And we want to compute the probability that it's actually 6. So this is the event, this is the probability that we want to compute. What is this? Probability of S1 intersection E, right? By probability of E. This is what it is, right? Now if you think about it, this again I can rewrite this as probability of E into probability of, let's rewrite it differently, because look at this. If you think about it, I have actually probability of S1 and probability of S2 here. I have these probabilities. So if we rewrite this as probability of E given S1 and probability of S1. Look at this. If I write it this way, this is nothing but E intersection S1 by, now what is probability of E? Now E, the man says dice is 6. This can happen when actually dice is 6 or when the dice is not 6. So this is nothing but probability of E intersection S1 plus probability of E intersection S2. Because S1 and S2 are mutually exclusive and exhaustive. Right? Now what is this? Now if I expand on this, what is this? This is nothing but probability of E given S1 multiplied by probability of S1 divided by, again this I can rewrite just like the numerator, I can rewrite this as probability of E given S1, probability of E given S1 into probability of S1 plus Again, I can rewrite this as probability of E given S2 into probability of S2. Again, simple Bayes theorem. I'm not making it any complex or fancy. Now let's put in the values. Now let's plug in the values. What is probability of S1? It is 1 by 6. This is also 1 by 6. Probability of S2? Probability of S2 is 5 by 6. Very good. What is probability of E given S1? See, what is E given S1? S1 basically means, if you think about it, what does S1 means? The dice is actually 6. The dice is actually 6 and the man says it is 6. We know the man says truth only 75% of the times, right? So what if it is actually 6 and the man says it is 6? That is 3 by 4, right? So this is also 3 by 4 now, this one. Now this is the exact opposite. This is, the dice is not 6, but the man says 6, which means he is lying. With what probability this happens? This happens with 1 by 4 probability, right? Very simple. Now if you simplify this whole thing, you have 3 by 4 into 1 by 4 by 3 by 4 into 3 by 4 into 1 by 6 by 3 by 4 into 1 by 6 plus 1 by 4 into 5 by 6. If you simplify this whole thing, you get 3 by 8, right? So this is a simple application. If you just define these three events and if you see what you have is PS1, PS2, you have PE given S1. This is easy to compute. You have PE given S2. These are the four things that you have. Now this probability, this conditional probability, you have to express it using these four expressions, or using these four expressions for which you have the actual values. That's it. So this is 3 by 4 and this is 1 by 4. That's it. Using these four. So now I broke it into step by step, and step by step I arrived at this equation. And this is just repeated application of Bayes theorem, nothing else. Simple, straightforward question. But the challenge here is to write this first equation and to realize that these are the four values, or these are the four expressions for which we know the values. Okay, very good question. So now let's look at this question 14, right? It says the probability density function of a continuous random variable x that ranges from 1 to e square. So the random variable x itself takes values from 1 to e square. E is the base of the natural logarithm. Is given by fx equals to 1 by x, right? So we are given this. Very good. Find the value of k such that probability of x greater than k equals to 0.1. Okay, that's what it says. Now how do we solve this? Okay, it's a simple problem if you think about it. So okay, so the variable itself, the random variable itself takes values from 1 to e square. So we want to compute probability that x is greater than k, right? So this I can write it as integration of fx, right? If you think of it as area under the curve, right? Imagine if this is my f of x. Okay, I'm not drawing the exact f of x here. If this is my f of x, let's assume this is my f of x, right? If I want to find a value such that probability that it is greater than k, right? I just have to integrate it across all the possible values. Let's assume this is the maximum value e square that I have. Again, I'm not drawing 1 by 2x here. Given any probability density function, if the maximum value is e square, to compute this probability is nothing but like computing the integral, right? Very simple question here. Again, we have seen this in the course videos, right? So probability, so it is integral of fx dx from k to e square, because the maximum value is e square, right? This integral is equal to 0.1. Now we have to just solve for that integral. We know f of x, right? So what is f of x? This is e square. F of x is 1 by 2x. 1 by 2x dx. So 1 by 2 is constant. Integration of 1 by x is log x, or natural logarithm of x, right? So this in the range of k to e square is equal to 0.1, right? This is what it is, right? So if I now simplify this, log of e square is equal to 2. So 2 by 2 is 1. 1 minus log k by 2 equals to 0.1, right? Now what is k now? So k equals to, so if I bring this side, so log n by k, log k by 2 is 0.9, right? 0.9, right? That's what it is, right? 0.9 and 2, 1, and so I get this side, I take this that side, yes. So now what is log k? Log k is 1.8. So what is k? K is e power 1.8. Now if you notice all these options, this is e power 1.8, right? So option D. So very simple question if you think about it. All you need to know is how do you compute this probability? If you can write from this expression, if we can realize that this is equal to the integration of PDF, it's integral of PDF from k to e square, because again, e square is the maximum value. The moment you realize this is a very simple problem of integration, right? Again, what I've described here is something that we have discussed extensively in the course videos, right? So now let's look at this question. It says a biased coin, which means the probability of heads and tails are different, is tossed repeatedly. Assume that the outcome of different tosses are independent, right? And the probability of heads is 2 by 3, which means probability of tails is 1 by 3. What is the probability of obtaining even number of heads in 5 tosses? See, we are counting the number of heads in, we're counting things like k heads in n tosses. This should remind you of your binomial random variable, right? This should remind you of your binomial random variable, because that's what it is. So you're doing 5 tosses, so n equals to 5, and you want even number of heads. So your k can be 0, or number of heads can be 0, your number of heads can be 2, number of heads can be 4. There are 3 possibilities here, right? And the probability of head itself, which is your p, like if you think about it as a binomial random variable, right? I want to see how many ways, so this is my binomial random variable with p equals to 2 by 3. So if x is my random variable, which is the number of heads in 5 tosses, right? So this is my n now. So now it's asking probability that x equals to 0 plus probability that x equals to 2 plus probability x equals to 4. And x is a binomial random variable here with p equals to 2 by 3. And we know the properties of a binomial random variable, right? What is this? This is nck. This is nck 2 by 3 power k. P power k, right? So p power 0, p is 2 by 3, 2 by 3 power 0, and 1 by 3 power 5. Plus, because this is 0 heads, right? This is 0 heads. Now this is 2 heads. 2 heads in 5 choose 2 ways. 2 heads and 3 tails, right? Plus, this is 5 choose 4. Again, this we have discussed in the binomial random variable, and how we compute this, we discussed it in the course videos for binomial random variables and binomial distribution. So 5 choose 4, and I want 4 heads. So 2 by 3 power 4 and 1 by 3 power 1. Now, of course, this is computationally slightly tricky to compute, but if you just simplify this whole thing, you'll get 121 by 243, right? So I'm leaving that simple computation because you can just use a calculator and quickly compute everything. So the right answer here is 121 by 243.